Imagine the most advanced fighter jet ever built, the F-35 Lightning II, a marvel of engineering, a symbol of American air dominance. Now, imagine it's grounded, not by enemy fire, but by a command sent from halfway across the world. A digital kill switch, embedded in a microchip smaller than your fingernail, has just rendered a multi-trillion-dollar weapons program useless. This isn't science fiction. It's the nightmare scenario that triggered a quiet panic inside the Pentagon, and it's the secret origin of the US-China tech war. For years, the headlines have sold a story of economic competition, a battle for market share and technological leadership. But what if that's not the real story? What if the primary driver isn't Wall Street, but the Pentagon? How did the world's most powerful military become terrifyingly dependent on a supply chain running through its main adversary? And what is it doing to claw back control? This is the untold story of the real driver behind the US-China tech war, a secret conflict waged not for profit, but for military survival. To understand the Pentagon's current panic, we have to go back to a time when the relationship between the military and the microchip was entirely different. In the 1960s and 70s, the Department of Defense, DoD, was not just a customer of the nascent semiconductor industry, it was the customer. Its insatiable demand for smaller, lighter, and more reliable electronics for missile guidance systems, like those in the Minuteman II, was a godsend for fledgling companies like Fairchild Semiconductor and Texas Instruments. During this golden age, the DoD accounted for over 50% of the total market for integrated circuits. This immense purchasing power gave it unparalleled influence. The Pentagon could steer the direction of technological development, paying premium prices for early access to cutting-edge chips that allowed it to miniaturize and harden its weapons systems. This government-funded demand created a fertile ecosystem for innovation. The military even mandated knowledge sharing among competitors through policies like second sourcing, which required a primary contractor to license its designs to a competitor to ensure a redundant supply. In effect, the DoD was the engine of Silicon Valley, and national security was the fuel. But then, the world changed. The commercial market for electronics, driven by everything from calculators to personal computers, exploded. The semiconductor industry grew at a blistering pace, and the DoD's role began to shrink dramatically. By the end of the 1960s, military purchases, once the lifeblood of the industry, had already fallen to less than a quarter of the total market. As the commercial sector boomed, the Pentagon's needs and the industry's priorities began to sharply diverge. The military required small batches of highly specialized, durable, and often radiation-hardened chips designed to function for decades in extreme environments. The commercial market, in contrast, was a high-volume game, chasing economies of scale to produce cheaper, more powerful chips for consumer gadgets with product life cycles measured in months, not decades. The DoD became a low-volume, high-maintenance, and relatively unprofitable customer. The numbers tell a stark story of diminishing influence. Today, the global semiconductor market is a $527 billion industry, and the DoD's share has plummeted to less than 1%. It no longer has the market power to command the attention of leading-edge suppliers, who are far more focused on the massive orders coming from companies like Apple or Nvidia. This shift was accelerated by a deliberate policy change within the Pentagon itself. Beginning in the 1990s, a memo from Secretary of Defense William Perry directed the military to use commercial off-the-shelf (COTS) products wherever and whenever possible. The goal was noble: to save taxpayer money and speed up the painfully slow development cycle for military hardware by leveraging the rapid innovation of the commercial sector. This calculated gamble prioritized short-term economic efficiency, but it came with a hidden, long-term cost. It tethered the entire US defense industrial base to a global commercial supply chain that the Pentagon no longer controlled. The bill for that decision is now coming due. Decades of this fabulous military strategy, combined with the relentless corporate pursuit of lower costs, led to the widespread offshoring of semiconductor manufacturing. The labor-intensive stages of assembly, testing, and packaging, ATP, were the first to move to Asia in the 1960s and 70s, establishing a trend that would eventually see the entire production process globalized. The result is a modern supply chain so fragmented and complex that it represents a nightmare for military strategists. To understand the scale of this vulnerability, let's trace the globe-spanning journey of a single critical chip inside an F-35 fighter jet. First, the design. In Silicon Valley, a US company like Xilinx, now owned by AMD, designs a highly advanced field programmable gate array, or FPGA. These chips are essentially programmable processors, crucial for the F-35's sophisticated avionics, its communication and navigation systems, and the real-time digital signal processing that allows it to fuse data from dozens of sensors into a coherent picture of the battlefield. Second, the fabrication. The digital blueprints for this American-designed chip are then sent to Hsinchu, Taiwan. Here, in one of the most advanced factories on Earth, Taiwan Semiconductor Manufacturing Company, TSMC, turns the design into physical silicon. This is the most critical choke point in the entire global supply chain. TSMC alone produces over 90% of the world's most advanced logic chips. If you want the best, you have to go to Taiwan. There is no other option. Third, the packaging. The finished silicon wafer, containing hundreds of individual chips, is then shipped to an outsourced semiconductor assembly and test OSAT facility. The world's largest OSAT providers are all located in Asia, with major hubs in Taiwan, mainland China, and Malaysia. Here, the wafer is sliced into individual dies, which are then encased in protective packaging and tested for defects. A typical journey might see a chip fabricated in Taiwan, packaged and tested in Malaysia. Fourth, the integration. Finally, the packaged and tested chip is shipped yet again, often to a factory in mainland China, where it is soldered onto a printed circuit board alongside hundreds of other components. This completed board is then shipped back to a prime US defense contractor like Lockheed Martin for final assembly into the F-35's mission computer. This journey creates a strategic paradox of terrifying proportions. The very component that gives the F-35 its technological edge, an advanced FGPA, is sourced from the one place on Earth, Taiwan, most likely to be the flashpoint in a conflict with the very adversary, China, the jet was designed to counter. The operational readiness of America's premier fighter jet in its most probable combat scenario is therefore dependent on the physical security of its adversary's primary military target. For Pentagon planners, this isn't just a supply chain risk, it's a strategic feedback loop from hell. The geographic vulnerability of the supply chain is frightening enough, but what truly horrified the Pentagon was the realization of what an adversary could do with their access to the manufacturing process itself. The threat is not just that the supply of chips could be cut off, but that the chips themselves could be turned into weapons. This threat has a name, a hardware Trojan, or HT. An HT is a malicious, intentional modification to a circuit's original design inserted during the manufacturing process. Think of it like a spy secretly adding a few extra wires to a building's electrical plan. For years, everything works perfectly. But on command, those hidden wires can be used to shut down the power, leak sensitive information, or even cause a catastrophic failure. The globalized, multi-stage manufacturing process provides an adversary with numerous opportunities to insert such a Trojan. It could happen at the foundry in Taiwan, during the packaging stage in Malaysia, or even through compromised electronic design software used by the engineers in the US. These Trojans are designed to be stealthy. They can be as small as a few extra logic gates on a chip containing billions, making them nearly impossible to detect without a painstaking and destructive process of stripping the chip down, layer by layer, and examining it with an electron microscope. A process that is completely impractical for the millions of chips the military procures. The most terrifying application of a hardware Trojan is the creation of a kill switch. This is not a theoretical concept. It is a known capability that can be engineered into complex systems. An adversary could use an HT to create a hidden backdoor, a trigger that, when activated by a specific radio signal or a predetermined condition, could remotely disable a weapon system at the most critical moment of a conflict. The heavy reliance on reprogrammable FPGAs in systems like the F-35 makes this threat particularly acute. The very flexibility that makes these chips so valuable also presents a potential attack vector. If the chip's fundamental integrity is compromised, its programmability could be exploited by an adversary. This threat fundamentally inverts the traditional military-industrial paradigm. For decades, the primary risk was an enemy stealing your technology to copy it. The new, more insidious risk is an enemy building your technology for you, but with a hidden self-destruct mechanism. The security focus must shift from simply protecting intellectual property to verifying the physical integrity of every single component, a vastly more complex and expensive challenge. The danger extends far beyond a single component in a single jet. Modern warfare is a network-centric endeavor. The US military's power comes from its ability to link its assets, jets, ships, satellites, drones, and ground troops, into a single cohesive fighting force. A single compromised chip in one node of this network could potentially be used to inject malware that spreads across the entire system, creating a cascading, fleet-wide failure. This is not just paranoia. The Pentagon's own audits have revealed a shocking lack of visibility into its own supply chains. In 2022, the DoD was forced to temporarily halt deliveries of the F-35 after discovering that a magnet used in the engine's turbomachine was made with an unauthorized alloy sourced from China. The alloy had passed through 5 different companies before being installed. If the Pentagon's multi-billion-dollar acquisition programs can't track the origin of a simple magnet, how can they possibly guarantee the integrity of a complex microchip with a supply chain that is orders of magnitude more opaque? The COTS procurement model, designed for efficiency, created a trust deficit that the Pentagon now realizes it can no longer afford. It can no longer simply trust its suppliers. It must find a way to verify its components. Faced with this existential threat, the Pentagon began a quiet but radical overhaul of its microelectronics strategy. The goal: to build a secure, resilient, and technologically advanced domestic supply chain, a silicon fortress for the 21st century. This effort has evolved through 2 distinct phases, representing a fundamental shift in how the military thinks about technological security. The DoD's first major response was the Trusted Foundry program, established in the early 2000s. The program's objective was to create a secure chain of custody for the design and manufacture of critical military chips. It was a human-centric model based on trust. The Defense Microelectronics Activity, DMEA, would vet and accredit domestic facilities, ensuring the integrity of their people and processes. This program created a small network of trusted suppliers, most notably global foundries, which operates DMEA-accredited fabs in Malta, New York, and Essex Junction, Vermont. These facilities are capable of producing secure chips for a range of defense applications. But the Trusted Foundry model had a fatal flaw. It couldn't keep up. The commercial semiconductor industry innovates at a relentless pace, driven by Moore's law. The cost of building a leading-edge fab has skyrocketed to over $20 billion, an investment that can only be recouped through massive production volumes for the consumer market. The DoD's low-volume, specialized needs couldn't justify such an expense. As a result, the Trusted Foundry facilities were consistently 1 or 2 generations behind the state-of-the-art technology available from commercial giants like TSMC. The Pentagon was faced with an impossible choice: use secure but technologically inferior chips, or use advanced but potentially compromised commercial chips. Both options were unacceptable. This dilemma forced a strategic pivot. The DoD realized it needed a new model, one that could securely leverage the best commercial technology without having to build a completely separate and perpetually outdated military-only ecosystem? The answer was the Rapid Assured Microelectronics Prototypes Program, or RAMP. RAMP represents a paradigm shift. Its core objective is to enable the DoD to use state-of-the-art commercial foundries without depending on a physically isolated, closed security facility. It achieves this by moving away from the old, human-centric model of trust to a new, data-centric, zero-trust model called quantifiable assurance. Instead of just trusting the factory workers, RAMP uses advanced software, artificial intelligence, and secure cloud-based environments to verify a chip's design at every single step of the process. This creates a unique, evidence-backed digital fingerprint for each design, allowing the DoD to mathematically prove that the final physical chip matches the original secure blueprint. This new model is an admission that the DoD can no longer innovate in isolation. To maintain its technological edge, it must integrate with the commercial sector. This has led to massive partnerships with America's tech giants. Microsoft provides the secure Azure government cloud platform where defense contractors can design their chips in a protected environment. Intel, through its new Intel Foundry Services division, provides the DoD with access to its most advanced, US-based manufacturing processes, such as its cutting-edge Intel 18A node. This is a symbiotic relationship. The DoD gets access to world-class technology, while Intel and Microsoft secure a massive government-backed anchor customer to help them compete with their own rivals, TSMC and Amazon Web Services. The Pentagon's new strategy required a massive financial engine to make it a reality. That engine is the CHIPS and Science Act of 2022. While publicly pitched as an economic initiative to create jobs, fix pandemic-era supply chains, and boost U.S. competitiveness, its core purpose, from the perspective of the defense community, is unequivocally about national security. The statements from military leadership could not be clearer. In a joint letter with the Commerce Secretary, Secretary of Defense Lloyd Austin wrote, "Funding the CHIPS Act is critical to our national defense. Weapon systems employed on the battlefields of today and emerging technologies of tomorrow depend on our access to a steady, secure supply of microelectronics." He later added, "The investments made through the CHIPS Act are critical to our national security and will directly support maintaining America's technological and military edge." His deputy, Kathleen Hicks, was even more specific, stating that semiconductors are fundamental to a broad range of advanced Department of Defense capabilities, such as autonomous systems, artificial intelligence, directed energy, and hypersonic weapons. This isn't the language of economic stimulus, it's the language of a new arms race. The CHIPS Act represents the fusion of economic and military policy on a scale not seen since the Cold War. It is a formal declaration that in the 21st century, the security of the commercial industrial base is national security. A look at how the $52.7 billion in CHIPS Act funding is allocated reveals a clear defense focus. Beyond the general subsidies available to companies like Intel and Global Foundries to build new fabs on US soil, the Act carves out specific funds to be managed by the DoD for its unique needs. First, there is the $2 billion CHIPS for America Defense Fund. This money is being used to establish the Microelectronics Commons, a national network of 8 regional innovation hubs. This network connects universities, startups, and defense contractors to bridge the infamous Valley of Death between laboratory research and high-volume fabrication. Its explicit goal is to accelerate the lab-to-fab transition for technologies critical to the warfighter, such as quantum computing, 5G/6G communications, and AI hardware. Second, and even more direct, is the funding for the Secure Enclave program. This is a separate $3 billion initiative, also funded by the CHIPS Act, but managed by the DoD, which has been awarded to Intel. The Secure Enclave is designed to create a highly secure, physically isolated, foundry within a foundry, at Intel's US facilities. It is focused on creating an end-to-end production capability, specifically for the military and intelligence community's most advanced and classified semiconductor needs. This two-tiered funding structure directly mirrors the Pentagon's new security strategy. The Microelectronics Commons creates the broad, innovative ecosystem needed for the majority of defense applications. The secure enclave, meanwhile, serves as the modern, high-tech equivalent of the old trusted foundry, a fortified pipeline reserved for the nation's crown jewel components. From the Pentagon's strategic viewpoint, the entire CHIPS Act is a monumental national security investment. It provides the financial fuel for the RAMP program's key partners. It incentivizes the onshoring of the advanced manufacturing capacity that the military desperately needs. And it builds the research and development ecosystem required to ensure the US stays ahead in the technologies of tomorrow. The jobs and broader economic growth are welcome side effects, but the primary objective is the construction of a resilient defense industrial base capable of sustaining the US military through a prolonged high-tech conflict with a peer adversary. The ambition behind the CHIPS Act is immense, but its success is far from guaranteed. The plan to rebuild America's semiconductor fortress faces a formidable set of challenges, raising serious questions about its feasibility and potential unintended consequences. The first and most glaring hurdle is the staggering cost. The globalized semiconductor supply chain, for all its vulnerabilities, is a marvel of economic efficiency, honed over decades by the principles of comparative advantage. A full-scale attempt to create self-sufficient regional supply chains would require at least $1 trillion in upfront investment and would result in a 35% to 65% increase in the price of chips. The CHIPS Act's $52.7 billion, while substantial, is merely a down payment. Critics argue that this government intervention will inevitably distort markets, lead to inefficiency, and impose a hidden security tax on the entire economy, raising the price of every product that contains a chip, from cars to coffee makers. Some analysts contend that a more efficient strategy would be to deepen partnerships with trusted allies like Taiwan and South Korea, rather than attempting a costly and likely incomplete reshoring effort. Building factories is one thing, finding the people to run them is another. The United States is facing a critical shortage of skilled labor for the semiconductor industry. A 2023 report projected a shortfall of 67,000 technicians, computer scientists, and engineers by 2030, a gap that could leave the brand new, multi-billion-dollar fabs struggling to operate at full capacity. This is not a problem that money alone can solve. It requires a long-term, systemic overhaul of STEM education, vocational training, and high-skilled immigration policies, all of which are politically complex and will take years, if not decades, to bear fruit. Already, TSMC has cited a shortage of skilled workers as a reason for delays at its new Arizona facility. What good is a state-of-the-art fab if you don't have the workforce to run it? The CHIPS Act has also drawn criticism for potentially amounting to corporate welfare. The lion's share of the subsidies is flowing to large established companies like Intel, TSMC, and Samsung, the very firms that spent decades offshoring their manufacturing to Asia in the pursuit of higher profits. Some analysts point out that many of these companies have spent hundreds of billions of dollars on stock buybacks in recent years, money that could have been invested in domestic manufacturing. The concern is that taxpayer money is being used to reward the past behavior of incumbent firms, potentially stifling innovation from smaller, more agile startups that could be developing the next generation of semiconductor technology. Perhaps the most significant strategic risk is that America's aggressive push for technological sovereignty could backfire. The sweeping export controls and industrial policies aimed at hobbling China's semiconductor industry may ultimately serve to accelerate its own drive for self-sufficiency. By cutting China off from the global supply chain, The US is providing Beijing with the ultimate motivation to pour unlimited resources into solving its technological bottlenecks. While this will be an incredibly difficult and expensive endeavor for China, if it succeeds, the US will have inadvertently created a more resilient, independent, and ultimately more formidable long-term competitor, completely free from any reliance on Western technology choke points.